The title of tonight's talk is Resilience is the New Sustainability, and we're calling it a paradigm shift for architects. It certainly has been for engineers as well. And so let me just walk you through the agenda for today. We're going to start off, I will introduce our speakers for this evening, and then we will have a panel presentation by two of our speakers on the main topic. And then we're going to show you a case study, actually, of a project that is currently underway at UCSF Mission Bay, the Block 33 development. It's a very interesting project of how resilience was folded into the design of the project, both from the structural engineering side and the architectural side. And then we'll certainly have time for questions and answers, and then we'll just wrap up after that, okay? So if you have questions, please hold them till the end of the presentations, and then we'll just, we'll go through and ask as many as you'd like. So first, I want to introduce our speakers. The one gentleman who is on his way here is Michael Bidet. He is with UCSF. He's the Associate Vice Chancellor, in charge of all the capital programs. It's a big job. He's in charge of over 140 capital projects currently and several $1 billion worth of construction. He is a registered architect by trade. And he's been very involved in the various chapters of the AIA here and statewide. And then we also have David Friedman. David Friedman is a well-known structural engineer from Farrell Elsesser, was past CEO and chair of Farrell Elsesser, has been involved over several decades in many of the most important new technology projects using base isolation in San Francisco and the wider United States. He's also been very involved with EERI, been on the board. He's current president of EERI, and he's also involved in various philanthropic nonprofit organizations. And for David, resilience is not only the technical challenge, but it's also sort of the social challenge of making an improvement in social welfare. So, and he's also a member of the board of directors of the U.S. Resiliency Council. And then we'll have Brett Roberts. Brett, you want to raise your hand? Okay, Brett will be coming up here to talk about the case study project that I mentioned, Block 33 at UCSF. He's a registered architect, works with Smith Group. And he's going to be talking along with David about some of the interesting challenges and opportunities that were available on that project. And then let me just introduce myself briefly. My name is Evan Reese, and I'm the Executive Director of the U.S. Resiliency Council. I'm a registered structural engineer, cut my teeth at Degenkolb many years ago, and worked after the Loma Prieta earthquake. Focusing on seismic retrofit of historic structures primarily, and then risk modeling and risk management. And so I helped found the U.S. Resiliency Council along with Ron Mays, who is here, about 6 years ago now, I guess, to develop a process for educating the public and building stakeholders about the value of building performance and resilience. So let me just start off with a couple of thoughts before we move over to the presenters. Green design, LEED design, has obviously taken off since the early 2000s. When it was developed some 20 plus years ago, it was slow to take off, but the growth has been really exponential almost every year. And you can see the bar in green there are the number of LEED projects that have been completed from 2000 to 2012. That's obviously been a great boon for the environmental movement, for having less of an impact on the environment, using less natural resources. But the question that we often ask is it really meeting the sustainability promise? Is green design? What does sustainability really mean? No matter how little energy you might use in the day-to-day activities of a building, the biggest environmental cost of a building is always when it's built. Okay, that's the biggest environmental cost of creating the materials, shipping the materials to the site, and constructing them on the site. And so the more times you have to build that building, the less sustainable it really becomes. The blue graph represents the total cost, rough estimated economic cost of catastrophes in the US over that period. And as you can see, that's grown as well too. And those catastrophes obviously represent billions, even hundreds of billions of dollars of building damage, building-related damage, buildings that have to be repaired or replaced at huge cost, a huge cost to the environment. You have to take that material, do something with it, and then you have to build a new building in its place. And so, you know, the question I raise is, even though we've seen such a sharp increase in the amount of LEED certified buildings that have popped up around the country, we also are seeing a continued increase in the amount of damage that's being caused. So how sustainable really is that movement? And that's what we want to try and get at a little bit today. That's what the USRC is trying to promote. You know, I think the best example of this is probably Superstorm Sandy. So Superstorm Sandy, it hit the New York, New Jersey area, and there were more LEED certified buildings in the world in that area than anywhere else in the world. And so, you know, sort of the catchphrase that I use is that these buildings were designed to have a low impact on the environment, but not for the environment to have a low impact on them. And that's really the difference between something like just pure green design and true sustainability, true resilience. And you can see the cost of that event in terms of deaths, buildings damaged. Even if you look at just the amount of debris generated at the bottom, over 10 million cubic tons of debris were generated. And all that stuff has to be moved, stored off-site, will degrade somehow, and then, of course, generally it's going to be replaced with new building construction. So this is what we want to avoid. We obviously want to avoid, we want to have buildings that have low impacts on the environment, but we also want them to withstand the environment's impacts on them. So, you know, where I see us going here is a convergence between architects and engineers. We really want this, the concept of the U.S. Resiliency Council to be something that's embraced by the whole AE profession. Both architects and engineers used to design right based off of the code. They follow the prescriptive measures that were required in the code. And then architects, 20 years ago were starting to develop really green designs using LEED, using USGBC and other processes. And engineers, about the same time, were also doing something called performance-based design. We were also learning how to measure the performance of the individual buildings after an earthquake or other disaster. But I think we can combine that and really move forward one more step and start to focus on resilience-based design. So combining, green architecture and structurally resilient systems, and looking also at how that resilient design impacts the whole community. So, we talk a lot about hospitals. Obviously, a lot of us have worked on hospitals. We know why they have to be resilient. But, what do you think? What about a grocery store? What about a grocery store in downtown San Francisco where without transportation networks, it would be very difficult for somebody to actually go out and find food after an earthquake? How resilient should your grocery store be, or your housing for that matter, obviously, when you have people in the San Francisco Bay Area that are going to be displaced all throughout the Bay Area. It's not going to be easy necessarily to find housing. So the resilience-based design helps look at the wider aspects of the community as well as individual buildings. And so you can see from this little wheel that I put here, how traditional green design and performance-based resilient design should work hand in hand. So we want the goal of the U.S. Resiliency Council is to promote this across both disciplines of architecture and engineering. And so that brings me just quickly to the U.S. Resiliency Council itself. We were founded in 2011 as sort of an outgrowth of some work that the Structural Engineers Association of Northern California was doing to develop a way to measure and communicate building performance through a rating system to owners and buyers and lenders and those that might lease buildings. We're established as a nonprofit, and our goal is twofold. It's to promote the concepts of resilience, to educate the public and everyone that's involved in a building somehow, whether it be an owner or a tenant or a parent taking their kids to school. And also to implement a rating system. We have rating systems for everything in the world, right? We have rating systems for colleges, we have rating systems for cars, we have rating systems for green design, obviously, with LEED. We would like to see a rating system, and that was our vision, to see a rating system for performance of buildings in natural disasters. So we've started with earthquakes, we'll be moving on to hurricanes and floods, wildfires, and other disasters as well. We're proud to have 64 members that support us financially and have contributed technically to the development of the rating system, and 100+ other supporters that have endorsed us or are working with us in other ways. And there's a bunch of material out there on the front table for you to please take to learn more about the USRC. And our website, of course, is www.usrc.org. So finally, the goal of the U.S. Resiliency Council is to work in collaboration, essentially, with the traditional sustainable design of the USGBC. We would like to be able to say that where the USGBC leads in green and environmental design, we lead in performance-based and resilience-based design. And architects and engineers can work together to create buildings that encompass all of these metrics. Okay, so with that, I am going to turn the presentation over to Michael Bade from UCSF, who is going to give you a little bit of a background on UCSF's program for resilience.
Okay.
I'm going to give you this.
Okay.
And you don't have slides, right? So
no, I don't have slides.
You can stay there if you'd like.
Yeah, I'll just stay right here. Sorry I was late. We are extraordinarily busy over at my place, as some of you know. We have about a $2 billion capital program, most of which is going to get spent in the next 5 years. And I've got multiple new buildings in design and about to go into construction. So we're kind of tearing our hair out, getting everything ready. We started thinking seriously about resilience in 2011, and we decided to actually adopt a performance-based design approach for architecture as well as engineering. And we were doing an office building at Mission Bay. Some of you may have heard of Mission Hall. It has certain notoriety, but it was our first foray into a performance-based design approach. We worked with Gensler, and we developed a performance spec that covered the entire building design. It covered energy, it covered environmental sustainability, it covered structural durability and maintainability. It was a leap into the dark. And you know, once in a while one takes a leap into the dark. This was $118 million leap into the dark. And it actually turned out to be a fascinating exercise, and we learned a lot. It's a pretty darn good building. We got better than code structure. We got a really durable shell that was designed to the same level as the structure was, so that we wouldn't have a leaky building after a big earthquake. We designed the raised floor system to the same level as the structure, so that we wouldn't have a caved-in raised floor system after an earthquake. My campus leadership was quite happy with that, all of those facts, because Tulane University, after Katrina, lost the largest, one of the largest sample sets of blood samples in medical science, because the flood prevented the fuel tanks for the emergency generators from being replenished. And so they ran out. And then the freezers stopped freezing, and everything thawed. And it was a sort of a scientific catastrophe. And it, at least among some people at UCSF, it woke people up to what could really happen. The other thing that happened was their star faculty started being poached unmercifully by other universities. And so, you know, we started thinking about that too, because people will poach us after a big earthquake if our folks can't work. So one of my tasks now is to expand this performance-based design approach to all of our major new building projects and to our major renovation projects. We're going to show you, after David's presentation, a high-level snapshot of just what we've done with one of our projects and how little this can cost. One of the things that we've learned is having a building structure self-centered after an earthquake is a really great thing, because then everything's not out of whack and all of the waterproofing gaskets and joints and so on aren't stressed. We've adopted that approach as a watchword for, even if we're doing a code level design, and there are differences between within, code is a wide band, it's not a point target. Some code buildings perform better than others. Some structures are better choices than others for resilience. But even if you're doing a code building, having characteristics like, returning to vertical, which is possible to do now, as Evan mentioned, the tools for structural engineering are drastically improved over 25 years ago. These can be real boons. The approach that we're taking is holistic. We define a project cost target, and then we try to get everything that we possibly can across the entire spectrum of value in the building for that cost target. And as we go, we make choices about relative importance. But overall, what we're trying to do is to maximize value. And we use our performance specification as a way of measuring value. So the performance specification has tiers, and those tiers give our designers and engineers a framework in which to understand value to us and to design value for us. When the relationship between an owner and their designers and engineers and consultants can be really developed around value, that is the foundation for a lasting relationship. And so if you folks are really interested in forming lasting relationships with clients over decades, which is great business, this is stuff to pay attention to. And this material, this approach that Evan is describing and that David's going to talk about, and some folks from our project are going to talk about, can be the foundation of something that gives you a real foundation for practice in the best sense of the term. And it's really energized me. It gives me a way to talk to the folks that are working for us that's really productive and focused on what the very best possibilities from the design process are. Obviously, there's a lot of horse trading that goes on inside the design process within this sort of framework, where we have a dollar cap, we have contingencies for risks, and we have things that we as an owner have to spend money on, and then we have the building budget, and we do trade between those. If we can mitigate risks without a lot of cost, we can spend more money on the building, things like that. But that's just part of delivering a great project. But I think that talking to the people who do our design and engineering work, it's everybody that I've talked to has felt energized and engaged to a very high level through this new kind of structure that we're trying to develop. And I have to say, we did this with our Mission Hall project. That was version 1. Version 2 of our technical performance specification was for our Block 33 project. And version 3 we developed for a new neuroscience research lab that has a large clinical component in it. And that has been a challenge. And we're doing it all over again for a project that we have over at San Francisco General that we haven't hired anybody to do yet. We're just working on the programming. And so it's been a forced march to develop a technical performance specification that contains really measurable components that give people a way of evaluating what the value is that's being proposed. Sometimes we've been vague. We're really trying not to be vague. And when you're vague, you can't measure the outcome. So we're really trying to get this to get boiled down to only the measurable outcomes that the design teams can track easily and accurately. It's some folks say, and I believe this, that the hardest thing for an owner to do, a big complex owner to do, is to tell people what they want. This is an exercise in communicating what it is we want in a much clearer way. No owner wants to have a wreck of a building that nobody was killed in after an earthquake, especially an owner like us that's going to be here forever and needs to perform really essential public service. And so that's where resilience comes in. And so the methods that we use don't need to cost a whole lot, and they really reward people being clever and asking tough questions of us and thinking hard about what it is that is being proposed. Successful answers to those kinds of questions are really fun to find. And I think that everybody who's engaged in this fascinating and exceedingly complicated profession that we all share, that's why we're here. So with that, I'm going to turn it over to David.
Okay. So let's see, why don't you get the mic?
Turn the mic over to you.
Yeah. Great. So just use the left mouse key.
Okay.
I'll listen down.
So even though I've had a long practice of structural and earthquake engineering, I'm really speaking to you today as a board member of USRC and kind of an unabashed proponent of resilience. Resilience, and just as Michael was talking about, in a very holistic sense. We all were believers and are believers in sustainability. Unfortunately, sustainability forgot about earthquake performance. LEED really doesn't capture that, and one of the things USRC is trying to do is to try and provide that kind of methodology, that kind of rating system that incorporates all sorts of resilience, that holistic resilience, but also captures earthquake resilience in the process. I promise not to show you a single engineering slide during this presentation, but I've been, there's kind of 5 points that I want to make. I want to talk about earthquake risk. I kind of want to scare you a little bit because I'm not sure we're all quite scared enough about what the potential risk is. I want to talk about building codes, and this is all probably stuff you do understand, but I kind of want to swing the pendulum a little bit harder because I have this sense of urgency that we really need to pay more attention to it, because it's not only what the building code provides, it's what the building code does not provide, because it really only talks about life safety. I want to talk about structural performance goals for buildings, and then USRC ratings as a tool. Not necessarily as a design guideline, but something that can be used, that engineers have the tools now to begin speaking to issues of reducing damage and reducing downtime. And then again, kind of the urgency and kind of this need for seismic resilience from really almost a social justice perspective. Resilience is a measure of how quickly a system recovers from a shock. So I'm going to talk about kind of that earthquake shock and what we do. And we all know kind of the embedded energy and the embedded cost why we want to do this. We also know that there is that we want to incorporate all the broad definitions of resilience into the design process. Evan mentioned Sandy. We all are familiar with Hurricane Katrina and what happened to the city of New Orleans. Was not a very resilient response. Not just because of what happened to buildings like the Superdome, but when you have a population that moves completely and totally out of a city, it's really hard to economically recover. And those are the things that are being discussed by chief resilient officers all over the globe about how can we make a more resilient community. And I think that's probably the message that I want to convey the most is that it's not just seismic resilience that I'm after community resilience. I think that's what we're all trying to achieve. We have to consider all of these things. I had the opportunity to meet the chief resilience officer in New Orleans. He has 24 components to resilience. And one of them actually is not earthquakes, but thank goodness they have one thing that they don't have to worry about. I want to talk a little bit about risk. I don't know how many architects have seen this USGS posting on the probability and the risk. Anybody seen this before? Few people. So what it says is there's a 72% chance of a magnitude 6.7 earthquake or greater that will happen by 2043. 72%. This figure, when I first started showing this slide 10 years ago, it was 58%. The probability keeps going up. Now, it may not happen, that earthquake may not happen in my lifetime, but it's going to happen in the lifetime of the buildings that we're designing and building today. And that's why it's so important. We have had 2 reminder earthquakes, at least in my career. 1989 Loma Prieta, a more recent 2014 Napa earthquake. These were pretty small events. Wasn't such a small, 89 was not a small event for Santa Cruz, but it was really a small event for San Francisco. I don't know if you can read these. These are strong shaking. Maybe can we reduce the lights just a little bit, because I think I kind of want you to see these, because I'm making a point about these shake intensity maps. These are both the upper right one is for Loma Prieta, and you see the black line, which is the fault rupture, and the red zone is the strong ground shaking. Look at San Francisco, look at the East Bay. Very little ground shaking really in those areas. Napa, very isolated. It's kind of the map is to the same scale, but you can see it was pretty significant for Napa, but not for the region around it. Here is the ground shaking risk for the Bay Area. Look at the red zone there. This is what we're afraid of. This is what we're going to get. I can't promise you it. We don't exactly know where it's going to be. This would be the strong ground shaking from a repeat of the 1906 earthquake on the San Andreas Fault. And look at the extent of that ground shaking. So we're not talking about kind of a Santa Cruz event. We're not talking about a Napa event. We're talking about a regional event. And that's what the important thing we need to consider. This is the scenario for a Hayward fault. This is actually the scenario that we all think, or the seismologists think, are the likely earthquake we are going to have. And just one slide in red are the liquefaction zones in the Bay Area. It's almost synonymous with the zones in the Bay that are most vulnerable to sea level rise. And as I will say, some of those zones are also some of our most disenfranchised neighborhoods and communities in the Bay Area. And I guarantee you those are going to be the ones that are hit the hardest by the earthquake. The building code. The building code, I'm sure even architects know, is a minimum code for earthquakes. It's a life safety code. That's all it is. What does it mean? It means that it's designed so it doesn't collapse, protects life safety, and there's safe egress out of the building. It says nothing about what condition the building is in. It could be a complete economical loss, but that's a code design building. This slide just depicts that kind of what we engineers think about as safety is a code-based design, but why resilience-based design really needs to capture damage and recovery. We have an analogy of a crumple zone in a car. Cars are in a collision are meant to absorb the energy and crumple in response to that energy. That's somewhat what we structural engineers do for buildings. But again, it's an acceptance of damage. And I don't know how many people really realize that a code design accepts damage, accepts a lot of damage. So this is a favorite slide of mine. I was on a reconnaissance team to Kobe, Japan in 1994. This is a concrete frame building. How many of you think this is a code design? It is a code design. To how many of you is this acceptable? Come on, everyone should go like this. This is not acceptable. This is just absolutely not. This is certainly not repairable. That even though these shear cracks you could stick your arm through, we design buildings to accept shear cracking, and they can be harder to repair. We also need to look at and understand non-structural damage, and this is what Michael referred to and what Evan referred to as well, is even if the structure survives and does what it's supposed to do, we can get a lot of damage inside to the contents of the building, and that pretty much can destroy the functionality of the building. And it takes a long time to repair that, to clean it up, and to get it back in shape. Some of these photos are from New Zealand, where aside from how the building structure responded, look at the content damage and how functional are those buildings, how resilient are those buildings? Not very. We talk about structural performance in terms of 4 levels. Well, really mainly 3 levels: operational, negligible impact; immediate occupancy, safe to occupy, possible cleanup and quick repairs; and then the code, life safety. Collapse prevention. I'm not sure where we invented collapse prevention, and I'm not sure it's so acceptable to really design buildings to collapse prevention. I know how it crept into our vocabulary in performance design, but I'm not sure, again, that that's really acceptable to any of us. We do have new tools that we can respond to and really put some real strong metrics around performance of the building. We can really look at how can we reduce the amount of repair time, how we can reduce the amount of damage, and how we can restore buildings more quickly to be operational. Again, this evolution of the A&E professions, we started with a code-based design. Sustainability also led to performance-based design. Now we really do have these tools to do resilience-based design, and it is a holistic process. And Michael described it, and the case study will show it into a little more specifics about how it starts from the beginning and how the cost premium can really be minimized within the process. The USRC rating was meant to look at safety, damage, and recovery, all three of those. Some of us call it death, damage, and downtime because it's easier to remember. We look at 3 dimensions, and within each of those dimensions, we have a 5-star system that can really break down and target what kind of performance you would get. Repair cost the same way, downtime the same way, and there's a considerable rigor that goes into this process. A code-based design would probably be a good code-based design, 3 stars, 3 stars, and 2 stars. There is nothing wrong with a good code-based design. But what we need to start doing as designers together is to figure out and target what is the performance that we want the building to have, and then design to that. For community resilience, we're going to have buildings designed to all different criterias. But for it to be a resilient community, it needs to improve its combination of buildings that have more substantial responsiveness and resilience to an earthquake. Back to the 1989 earthquake. It was a good wake-up call for a while. I'm not sure today how much of a wake-up call it is. I don't know how many times in my career I have met a building owner that has said, but my building made it through the big one. What's the big one? 1989. No, it wasn't. And I almost, there was a time where it was a good reminder, but it's no longer a particularly good reminder. It was a good reminder for the city of San Francisco that embarked on how to make the response more resilient. It was called CAPS, the Community Action Plan for Seismic Safety. And they did extensive study. They looked at various scenarios, categorized what the losses would be, what the deaths, what the damage, what the homeless population would be, and then embarked on a program. I don't really expect you to read this, but it's a plan that started in 2010 and goes through 2040, and it's how to take on and reduce the risk to the city and county of San Francisco. Unfortunately, we're not very far along. We have recently, within the last couple of years, have a soft story abatement program. We have a new program around protecting K through 12 private schools so that they're built to the same standards or retrofitted to the same standards that public schools have been built to since 1933. The point of this slide is we're barely at the beginning of the work that needs to be done. And again, I'm a little impatient about how far we haven't gone yet. But the city of San Francisco has a plan. And gradually and slowly, we're getting there. I think we're more resilient than we were 5 years ago, but we're not necessarily as resilient as we would like to be. You're beginning to see these kinds of signs showing up around San Francisco because of the soft story abatement program. If they're not following suit, they have to post these warnings. These are the kind of rating systems we really don't want to see. But I'm not sure we really want to know at this point all of the hazardous buildings that really are in San Francisco. But going back, and this is my last slide, going back to the region and the social justice play of why resilient design is so important. I have spent a career chasing earthquakes around the world, and earthquakes are uncanny in their ability of finding weaknesses in buildings and hammering them. They're also uncanny in their ability to hit the most disenfranchised countries, like Katie, or communities that really cannot afford to rebuild. We see it in China, we saw it in New Zealand, we see it everywhere. You know, the same thing is going to happen in the Bay Area. It's going to happen in San Francisco again. It's better. They're doing things. UC Berkeley is doing good things. UCSF is doing terrific things. Stanford campus is doing very good things around resilience. But how about the southeast quadrant of San Francisco? How about East Palo Alto? How about Richmond? How about West Oakland? These are the communities that are going to get hammered in an earthquake. I can guarantee that. And that's our responsibility as designers, as architects, as engineers, to continue to try and build buildings and use ratings as a goal, resilience ratings as a goal, so that gradually we get to a more resilient community. So with that, we're going to talk a little bit about a case study.
Yeah.
And I think Brett is going to come up and join me.
Right.
Did you want to cover Steve's slides?
Yes, I think you're going to cover Steve.
Okay.
This should be the next slide.
And they should be, okay.
Yeah, so we're.
So Michael already gave a very good introduction to what's happening at Mission Bay. This Block 33 building, actually the person who was going to speak about this could not attend tonight, so I'm a fairly quick study, and I'm not totally involved in the project, but I think I can speak to where the project really started was a conversation about defining the resilience goals for the project. And it was to look at lower repair costs, reduce operational downtime, and consider structural and non-structural system performance. If I'm saying anything incorrect, let me know.
No, you're saying it great. And so let me just, David's going to talk about the structure, and Brett, who is here from Smith Group JJR, is the technical architect on the project, and he's going to talk about the shell. And I thought that it would be a good introduction to following a path of thinking through a building design. And I think we'll have a little bit of information about the cost premium, the minimal cost premium that this engenders. So.
Right, I think I have that. So step one was, and this was a project that at the RFP stage, as I understand it, even laid out what the performance goals for the project were. Is that correct?
That's correct, yes.
And this is kind of just another slide that, to somewhere in this, this continuum right here, the desire was to be to the left-hand side of the performance spectrum.
But we didn't know at the outset how far our money would take us. And so it's been a bit of an adventurous journey, but we're happy with where we're at.
3 tiers were defined for consideration. Tier 1 was a code minimum design. Tier 2 was a reduced damage at the code level earthquake, and Tier 3 was a reduced damage at the maximum expected earthquake level. And there were, tier is used in another sense here, but there were really 3 structural enhancements. And again, the red line was the code performance, and then there was the kind of 2 other tiers that had various degrees of enhanced structural performance or structural member capacity to try and stiffen the building and reduce the amount of drift, because drift is what causes damage.
So just go back. What's really interesting in the first slide,
the right-hand key.
Yeah.
The right-hand mouse button. And then go to previous.
Yeah. So look at the M7 on the San Andreas and the code level DBE, Design Basis Earthquake, and look at how close together the blue and green lines are in that zone. And then they don't diverge nearly as much to the M8 on the San Andreas as the two lines diverge from code. And this is in part a feature of the better soil conditions on the site that David should get into. But you know, this it really does illustrate for many sites that have reasonably good ground soil conditions, how close the two higher tiers can actually be together, and why it's worth pursuing this.
Which is the next slide, and Michael referred to this earlier in his comments, which was, you know, we can capture the incremental costs, and not only looking at the superstructure cost, but the additional soil improvement that was done that also led to enhanced seismic performance. And the tier 2, I believe, was the kind of the selected target, and I think the cost benefit in you know was maybe marginal incremental performance with an additional $600,000-700,000 of cost. This is just structure, and I know they're looking at non-structural systems, and you're going to talk about the cladding, but there's also mechanical equipment and partitions and other things that also the impact on them is reduced if the building is kept stiffer and the soils are more absorbent to the shock of the earthquake. And here, I think the noted point was the $900, less than $1 million premium on a project construction cost of $150 million or 165, or a total development cost of over $200 million. There's certainly a good holistic life cycle argument that can be made for, you know, why does an owner want to do this? Doesn't want to repair it later on, doesn't want to go to the embedded energy cost of having to redo this building again. The cladding performance was also looked at exhaustively in terms of this, in terms of looking at what the deformations in the structure were going to be and what the cladding system selection would be, and how to keep the envelope, the enclosure, watertight for a design basis earthquake. And that became a you know, again, the important interaction between engineer and architect, just as we know that building configuration, architectural shape, and seismic performance are inextricably linked. And so as we go through not only primary structure, but the envelope systems and all of the other systems in the building, resilience continues to play an important role in the dialogue between designers. So that was my segue to you, Brett.
Perfect. You got it exactly the right slides. That's ideal. Oh, look at this. Thank you. Okay, how's everyone doing tonight? Still awake? All right, I'll see if I can change that. Okay, so this is a great slide because I think the yellow zone is really ideal, because this is really what we're talking about when we're saying the sort of moderate event resiliency. And you know, we're saying that this building can shift side to side, in plane and out of plane, 1.5 inches in each direction, and still remain watertight. I mean, that's the goal. And that's easier to state than do, because not only are we out in front of code, we're actually out in front of manufacturing. So manufacturers don't necessarily make systems that handle that with the kind of warranty that most architects would expect. So when we're doing this, we're actually hand in hand with a lot of manufacturers right now to say, well, what do you think about this? How's a good way to proceed in working through this system? All right, so I'm going to...
No, not mouse, but...
Well, I'm going to be analog. Can I use the All right, I'll use this. All right. So as you'll see later, I have a kind of an antediluvian posture towards technology.
Yeah.
So it all starts with design. And I think what I wanted to talk about is that, you know, when buildings are analyzed, they're sort of roughly rectangular, more or less understandable shapes, but that wasn't enough. We actually wanted to do some different things here. So these floor plates are rotated upon one another. And that's significant because the systems that are used to clad the building are not maybe the first choice for an ultimately resilient building. I don't mean that as a dig. It's just it's an economic driver. So instead of, you know, a complete unitized system which is designed to rock and actually can perform quite highly, we're looking at different systems. We're looking at a stud-supported system, which is asking a lot of something like this. But then when you take that and you start to rotate the floors, it actually really asks a lot of questions about how and where we're going to accommodate drift in floors. A lot of times it's done at the underside of slab, but that's difficult when the slabs are jutting out and we've got architectural elements that are coming together right at that zone. So it actually confused it a little bit. So what we ended up doing, so I should also state that this started as well, it's not started, it's continuing as an integrated project delivery. So we've got other entities, fabricators, contractors, subcontractors that are really helping with this design. And so when we sat down with them originally, for various reasons, they all had different systems to propose to look at this system, to look at the building. So two major systems, basically a precast system, ribbon windows, and then, as I mentioned, the sort of stud-supported aluminum panels, and with ribbon windows. But what I wanted to talk about here is that, you know, this was their first take, and I don't mean to make it the sides, but this was various subcontractors coming together using their systems. This is where they anticipated drift. The blue lines are the horizontal drift, and red lines are vertical to accommodate that horizontal drift. So when we go back to that 1.5-inch displacement, and that's the moderate event, that's the M7 event, most systems, you know, we can go in compression, like for sealants, you can go to 50%. So we're now talking 3-inch wide joints. So there's a lot of gaps in the building. And even though that might be sealant, as an architect, I don't like big wide gaps in buildings because I think they're unsightly, but I also think that it's also an opportunity for more weather penetration. So a lot of this discussion is how do we manage that? So what we kind of tried to do here is try to rationalize as much as we could about the joint system. So initially, for instance, the proposal was to start with a lot of unitized window systems, which were kind of strange. They're basically rocking systems, but when you put a rocking system within a translating system, you still have the things are bumping each other on the side. So we actually kind of dumbed it down and said, well, what if we just use kind of dumb, stupid window systems that translate the same way the walls are translating? So that eliminated to a large extent all the vertical joints. I mean, the need for enlarged vertical joints for seismic purposes. And, you know, basically did what most good architects do. We just tried to rationalize it and say, okay, let's just bring these things straight across. Now, we had some immediate challenges with the fenestration. If you go back to the previous slide, you know, because the windows are jogging up and down, the idea was that the joints also would have to translate upward around these jiggy-joggy windows, right? So, you know, the immediate question was, okay, how do we want to deal with this? Because these step downs actually create a lot more transitions and joining problems and actually performance issues later on. So what we tried to do, and this is where we get to the antediluvian part, is we just came up with concept details initially. And the idea is just, we want to get the trade partners to kind of put their systems in here. So we don't want to rigidly design everything because we're dealing with different sort of performance criteria for each contractor. So we got to be mindful of that. And it's really to bring these guys along with a concept. So the two basic systems I just want to show here, Precast is pretty straightforward because there's, it's a barrier system. We're looking at a translating joint, and that is going to equate into a pretty large joint. This was considered okay because where these occur are actually pretty high on the building, and so they're not as present at the scale at a lower level as they are up above. And needless to say, when you deal with a barrier system, this is kind of what you get if you want to use elastomeric sealants. The rain screen opportunity gave us a little bit more flexibility because our water line, our continuity line, is really at the face of sheathing, face of glass. So we kind of can treat the cladding as a concealing element as well. So whereas here we're using elastomeric sealants in a wide thing, we can't really, in a wide gap, we can't really do that with, sheathing on studs. So we're actually looking at silicone transition sheet, STS. Basically, it's sheet silicone. It's got a much greater movement capacity, probably 300 to 400%. And this is what's been used inside of curtain walls for quite a number of years. It's the way to transition between different units to keep them watertight. And the technology is pretty straightforward. And, it's glue and silicone, or silicone, structural silicone and silicone. I actually have some samples of this, and I can tell you just where they are on my desk 3 blocks away. But anyway, I think then the other thing we wanted to try to show here is, and this is sort of dashed in where the panels are. This is the window head where it steps down. So rather than kind of deal with that, we kind of treated it like what we do with unitized window systems is we kept the windows the same height, and we just overclad it with the aluminum cladding. And this allows us to maintain a consistent joint. And so that doesn't have to move up and down, which means we don't translate vertically at all in the system. So it's nothing really revolutionary, but it did help free up the trade contractors to look at this and think about it a different way. So this is a kind of a section through that spandrel condition, and this is the plan condition. We're just basically using the window wall to support, or the window to support cladding elements. It's not really that revolutionary, but I think it kind of shows that the kind of holistic thinking that Michael was stating is that you really have to kind of look at these systems, understand the design objectives, and see how best we can make these work for us. And so I just wanted to close, and then we'll stop looking at old drawings. Because it's a translating system, at the corners we have to treat it like we would precast. In other words, when the building is moving, this wall, for instance, in one direction is moving like this, whereas this one is going to tilt. And so you're going to get a scissoring action right across this joint, similar to what we do in precast. So I think everyone knows once you turn a corner with precast, you're always faced with a larger joint than you'd like, but that's what we have to deal with. But here again, we're using the silicone transition sheet behind the rain screen. Because this is an open jointed system, we don't necessarily need to have to expose that as that wide joint, so we can conceal it. So we thought we'd be very clever there. And then that's going to interface with the horizontal joint at every floor, because these things are going to be at every corner. But again, silicone can lap over silicone quite simply, and it actually maintains its resiliency. This is the condition at the ribbon window where it turns the corner. Here, we do have to accept a larger joint. Again, the STS is really not too pretty to look at unless you like Band-Aids on buildings. So we try to, we have to countenance a larger joint there. But still, I think it's a pretty good trade-off for what we're getting. I should say that, the part about working with the manufacturers here is, though we're going to send this thing through a real performance mock-up, we're actually extensively sitting down with manufacturers right now and coming up with laboratory tests that we're going to do in advance, because this is the part where the guys that make this, Dow, they don't use it for this kind of situation. It's not something that they're marketing as a system, but we're going to look at just what sort of movement this can take, how much adhesion we need on each side, how wide the silicone transition strip needs to be, whether we create bellows to give a slack zone so it actually doesn't put the silicone in any stress? These are all kind of questions that we need to answer before we get to the mock-up. But that's just sort of an aside. I just didn't want to make everyone think that this was just you go to the store and buy this stuff. It does require a little bit of work still. With that, I was told to keep it short. Did I do that?
Yeah, that's great.
Okay.
That's great. Perfect.
Can I ask Brett a question?
Absolutely.
Just because it sounds like, I mean, this is some pretty creative detailing that you did. It was more driven by geometry and that which you were doing, that had this been a code level design, the building inter-story drift would have been greater. In fact, is it not somewhat true that by going to a higher performance structural design that made the building stiffer, at least helped you in terms of keeping some of the joints more of at a scale that you could deal with the detailing?
Absolutely. Yeah, that's very much the case. I mean, you can see that especially in the M6 event. It's only a ½ inch adrift, which I do hospitals, and I can't accept a ½ inch adrift. I mean, I'm used to seeing a lot more.
Right.
So yeah, the stiffness definitely helps.
Great. You are just,
One way or the other.
Yeah, this way.
I'm out of here.
Okay, great.
All right.
Stay close by. You might have a question. Okay. Well, first of all, I really like to thank Michael and David and Brett for the presentation. I think that gives you a really solid flavor of how an owner, an architect, and an engineer start with a criteria, start with a goal, a mission in mind, a vision for how this building is going to perform, not just every day, but after major earthquakes, and how important it is for those three groups to work together, not only from a cost perspective and a schedule perspective, but how the structure integrates with the architecture and how they work together to form something that is going to meet those performance goals. So that was really excellent. We're going to open it up to questions, but before I do that, I actually wanted to have a couple thank yous. I wanted to thank SOM for the generous donation of this room tonight and the snacks and drinks behind us. I want to thank you very much. Peter Lee, are you here? Yes, Peter and his group have put this all together for us, so we're very appreciative of that. And I'd also like to give a shout out to Margie O'Driscoll. She's in the back. That's about ready to send her kid off to college, so she'll have to head out. But before she did, I just wanted to thank her for coordinating all of the effort with the AIA California Council. And if you are an registered architect and you have not signed up out there, if your name, not everybody's name is going to be on that list because some folks signed up for multiple people, so I just have a number of tickets. But if you would put your name on there or on the back, and make sure that you put your email and your AIA number, you will get some continuing education credits for this too. Okay, so thank you, Margie, for doing all that.
One quick question.
Yes.
We had a question from one of the attendees that said it's a 2-hour-long seminar. How come they're only getting 1 hour credit?
I was only joking, Peter.
Well, the people that really know what they're doing only talk for an hour. Me, I'm just kind of giving you the fluff in the introduction. I guess maybe that's the reason. So at this point, I'd like to open it up to questions for any of our panelists or about the U.S. Resiliency Council. Yes.
I've got a question, Mr. Friedman. You stole my question, first of all, and it was a great question. But as a follow-up, it does introduce a lot of complexity when there's a lot of story drift detail in the curtain wall. So has anyone looked at the premium that it would take to increase the rigidity and stiffness of the structure to kind of minimize the story drift as it affects the cladding?
The reason I asked the question, probably would have been posed better by you than me, was just to really highlight that sometimes structural performance doesn't have to cost more, or there's the beneficial element to the collaborative design that with the geometry of the building would have been pretty hard to come up with some of those details at twice the drift. Right? I mean, I think it would have been difficult.
for it.
But sometimes seismic performance can help solve architectural problems. How to quantify some of that, I'm sure it can be. I'm not sure the best way to answer your question, but I think there certainly are ways where those kinds of things can be captured, in terms of what the cost savings and ultimately what the life cycle costing performance is.
Yeah, and the question does always come back to that anyway. Right.
Let me tag on to that. I mentioned that system selection has a big effect. We're finding that for a major lab building, a flat slab structure with no drop caps allows all the surfaces to be bolted tight to the slab, and it eliminates the pendulum effect. And so we're totaling up the cost savings, but it's rather dramatic. And another thing that's sort of directly related to that, if you look at earthquake damage insurance claims, both Napa and Northridge, 60% of the insurance claims were from water damage from broken pipe. And so that statistic had a huge impact on our thinking, given how many fluids we have running around in a lab building. So simple selection really, really changes the game if you're selecting with a holistic intent.
You might not be aware, but in an earthquake, a large earthquake, about 70 to 80% of the cost of damage is due to non-structural components. Everything from the mechanical equipment to the partitions and windows, with the remainder being the structure. So controlling non-structural damage is crucial, and that's generally the purview of the architect, again, working with the engineer to make sure the structural system is right.
Can you circle that back into reduced insurance premium?
That is something that the USRC is working really heavily on right now. Is we have several insurers that are collaborating with us to do. We're doing studies with some of their buildings to look at how different USRC ratings can reduce their actuarial losses and thus reduce the premiums. Yes, that's the goal. Ruth?
I was just going to ask if you could prioritize product manufacturers that you could target to provide increased resiliency, what would they be? Well, for instance, I just heard the mechanical
Right.
connections of systems, or whether it's this sheet rubber stuff, or if you could recruit those manufacturers to your board, which ones would you call first?
One of the software tools that we have now is called P58, FEMA P58. It was developed over 10 or 12 years, cost $10+ million. It was sponsored by FEMA, and the purpose of that was to develop tools to more accurately determine not only the total amount of damage that you would get in a building, but where that damage occurs. And what we found, for instance, is that substantial amount of non-structural damage occurs in partitions. Okay, and so working with partition manufacturers to make better designs to accommodate that drift would be one big way to reduce damage. And another large component was glazing. Okay, and so we talked about a bit about that today. So so this tool, FEMA P58, where we work with a lot of structural engineers, but also a lot of folks that were expert in non-structural performance, were able to now determine what kinds of non-structural components cause the most damage and reach out to them. We have a number of, we actually have one of our members is a manufacturer of seismic joints, exterior seismic joints. Because obviously those get beat up. I mean, they're intended to get beat up, but still, if you have a large building with a lot of seismic joints, reducing that damage or making them more, able to accommodate that drift without having to be replaced is an example of something that we use.
We're currently working on a project that has pop-open seismic joints that don't crush or damage. They can be returned to position as a mother cover.
Yeah. Okay, good. Yes.
This is sort of a historical question, but there was a lot of discussion about base isolation, which you mentioned early on, just after the Loma Prieta earthquake. And I heard anecdotally then that there was, that these base isolation systems were crumple zones and then needed to be kind of expensively rebuilt after an event. And I guess my question is, was that true, and is it still true that like base isolation is it a viable option still?
David. He knows a thing or two about base isolation.
It is still the best anti-seismic system I know. They don't crumple. In fact, if you think about a base isolator, and for those of you who don't know what a base isolator is, it's basically, there's two basic kinds. There's a rubber elastomeric bearing, bridge bearing, and there are friction pendulums. Those are kind of the two types that we have. And you can see them all over San Francisco, both kinds. They're kind of the favored structural system for hospital buildings, where that have to be essential services buildings that have to be immediately usable after an earthquake, operational after an earthquake. After the 1989 earthquake, there weren't really a lot of, I'm not sure there were any base isolated buildings in the United States before 1989. There were.
Yeah. Salt Lake City.
Salt Lake City.
In the San Bernardino Justice Center.
And that were done as base isolation retrofits. Salt Lake City was right. Some of the first buildings that we were involved with were base isolation retrofits of historic buildings, because there was really, and in the case of San Francisco City Hall, Oakland City Hall, the Asian Art Museum, this was really done to preserve the historic fabric of the building. They were brittle, and there was really no other way of strengthening those buildings other than inserting these base isolators in them. After an earthquake, because it's a newer technology, there is a requirement that the bearings have to be able to be tested. In the case of elastomeric bearings, they were concerned about an embrittlement of them. Should really let Ron Mays answer this question. But every base isolated building has the ability to take an isolator out and test it and bring it back. Most of them are expected to rate themselves. They're designed to rate themselves. So we don't anticipate damage to the isolators in large events. They do have a capacity in a maximum credible earthquake of potentially rolling over, and so many of the designs will have restraints on them so that can't happen, but that's in a maximum earthquake. So still, I would have to say, most of us engineers, and there are a few others in the room, that it's still one of the better anti-seismic systems we know of for high performance engineering.
Since you talked about the crumple zones, I think, there again, it's a lot of clever detailing and approach to how you look at that system. I still think probably the cleverest is the circuit court of appeals, where SOM used the actual architecture of the building. There's hardly any moats there because they took advantage of the fact that it was on a plinth, and instead of having a 3-foot moat, there's just a 1/4-inch gap. So it slides. So it's actually a really elegant solution, and it probably saves a lot of money.
Is that Peter Lee's solution?
I worked on that building
I know.
as well as.
You're buying me lunch next week.
Yeah.
So maybe I just might add to David and Brett's comments that seismic isolation will protect the overall building and greatly decrease the impact on the superstructure by taking the displacement that normally occurs at the roof of the building and concentrate that movement only at the base, so that the type of deformations that cause the non-structural damage that we talked about in the drift of the buildings occurring only at the base or primarily at the base. It never goes away completely. So studies that we've done in certain buildings would show that we might have a replacement for a code design building, as pointed out. We might have as much as 20% replacement cost of a brand new building after one of these major events for a fixed base, what we call a fixed base building, code design. And whereas a base isolated building may be reduced to 2.5% of the replacement cost for that building. And yes, it might be the crumpled zone of the moat around the base of the building where that 2.5% comes from. They may not perform perfectly. And so.
By design.
By design, yeah.
By design.
But by design. So, but largely you're protecting the superstructure from the type of inelastic deformations that occur in the structural system that would actually shut the building down. You would get red tagged or yellow tagged or red tagged so that you could no longer get continued operation. So seismic isolation brings you to that next level of seismic performance. That's not the only way to do it. There are other types of energy dissipating systems and strategies that go into buildings and structural systems that can be used to get a 5-star and a 5-star and a 5-star building.
Right.
So you have to look at these issues holistically, because we did a seismically isolated building, our stem cell building up on the Parnassus campus, used friction pendulum isolators. Dramatic reduction in structural cost. Instead of California-sized columns, we have Sweden-sized columns. You know, just the dramatic change in steel cost alone. You know, and if you are isolating your cost to of repair to easily procured elements which in no way compromise the functionality of the building, you can continue to operate it while you're waiting for repair. These are great things to evaluate holistically in a life cycle, continuous operation context, and you know, base isolators can really pay.
Well, I have a question for actually you, Michael. So when an architect or an architect and engineering team have their first sort of sit-down meetings with the owner, who should be in the room from the owner's perspective that are going to be able to help make that decision about whether to pursue this level of resilience-based design beyond just sort of quote the minimum code? Who should be there from the owner's side to help make that decision?
Well, I think that I've been supported greatly by our risk management people and our finance and budget people, because they know they're going to have to shell out a lot of money in the event of an earthquake that affects the university. The university is self-insured in many respects, not all. We are our own primary insurer for property, and then we reinsure, through Lloyd's and so on. But we're starting to think about how we can do exactly what the earlier question was going towards, which is, can we over time improve the performance of our building stock and lower our premiums, lower our expected cost of recovery, have greater continuity even for non-essential things that aren't involved with our hospitals. Berkeley did a study in the late 90s about the impact on the campus from a Hayward fault event, and it was in late 90s dollars, $2.6 billion and a year of downtime. That could lead to severe curtailment of the institution once competitor institutions start poaching star faculty and the students wander away and all that sort of thing. So you want to be engaged with people for whom those issues are things they worry about, right? You don't want to just have this all be tied up in the people who are trying to manage the first cost of the project to the lowest point possible. Because they're not going to be interested in, they don't care about the holistic life cycle cost context. So you have to find those other people and pitch the concepts to them and have work with them to develop the evaluative framework that you're going to use to make decisions on the project that are in support of these objectives.
Other questions? Yes.
This is a very different kind of question. I'm actually a mechanical engineer and energy analyst. And so I'm curious on, we talk about this holistic point of view, when you're designing the facade from both the seismic and structural side of things, but also from a passive design, because when I look at resiliency for like a hospital, we want to make sure that we can ventilate critical spaces in the event of an earthquake. And so how does that really impact the overall structural resiliency when you start factoring in something like operable windows or looking at your mechanical systems and how they sort of marry together with the building components?
Oh boy. Well, this building has clinical functions in it, so it falls under OSHPD 3, and you're probably aware of OSHPD's disposition towards operable windows. So that kind of comes off the table. I mean, I'd love that to change. That would be great. But because I have the window open in my office right now because I have it. But, you know, it doesn't just stop with operable windows. I mean, we don't just stop at resiliency. I think we have a fairly laudable sustainability goal, and I think a lot of the design is responsive to sort of reducing solar heat gain. I mean, you didn't see, I mean, these are very early sketches. It's not where we are right now, but there's a lot of elements incorporated in the building to kind of address that. But I'm not sure about the nexus with resiliency in a direct way.
Well, I can give sort of an example that an architect gave me, actually. So they designed a building that they were very proud of because it used recycled water everywhere. So it used very little water. The system then, you know, it does impacted the environment less because it used less water. But it was in the Southwest. And so the architect sort of turned it around. He said, okay, well, the Southwest is going to be seeing a lot more drought under climate change. So when there's drought and there's less water available, this building becomes more resilient because it uses less water. So, you know, so it's the trend for architects, mechanical systems designers to think about the things that they're already using to say, you know, to make a building have a lower usage and say, well, when climate change happens or when there's an earthquake and there's no power, there's another company that talked with us that creates batteries, okay? And so they have a process for delivering batteries to buildings after a power outage. So, you know, the things that you're already doing to think about sustainability, now think about them if those things that they use weren't there and how that benefits the building. When it comes to things like windows, it widens the circle of participants in those initial discussions. Okay, so you talk not only about the structural drift and the weatherproofing, but then how you're going to get ventilation into the building when the power's down, and you still have to be operable. Okay, so it just grows the circle of people and design professionals that should be involved in this whole resilience effort.
So one thing that we have in our technical performance criteria we use what we call an energy use index for the building that is based on actual data from our facilities and the local climate. And it takes process loads into account unlike Title 24. And we have 3 levels to the EUI. And people liking challenges, the architects and the mechanical engineers are designing the building to the most aggressive EUI target, which means that everything about the building has to contribute to that. The shell especially, because we're trying to minimize heat gain into the building. And we have a flat slab concrete structure that gives us nice thermal characteristics so the structure helps there. But I think that the answer to your question really lies, if you can do it right, you have to approach the entire building performance spectrum holistically. And for the owner to become explicit about that, that really helps everybody do a great job, because then, you know, they'll discover, our teams discover anomalies in our criteria. And so we clarify our criteria based on things people discover, and it becomes a two-way street, from criteria to design to thinking about possibilities to finding anomalies in the criteria, and so then we correct the anomalies. It's a sort of self-correcting process, but it's fun.
David?
Can I ask you a question?
Yeah.
You said that you have a 5-year building program of $2-point-something billion. Sounds like a lot of money. Do you report to a board of trustees? Do you have to explain to them what you're doing, what you're spending money on? Do you have people on that board of trustees that are developers who are telling you that you don't need to do this, or are you free and clear to do it the way you see is the right way to do it?
So UCSF, this is a little bit of a historical digression. When we first started developing our Mission Bay campus, all our big projects, save Genentech Hall, landed in litigation. And I came to UCSF in 2004, and my senior vice chancellor for finance said to me that you have to stop the bleeding, because we were bleeding money. And we had quality issues with some of the buildings too. And so since I had worked at the Office of the President prior, I had good relations there, and we had an in-house counsel. And so we won the ability of all the UC campuses to modify the design and construction contracts, to develop our own design and construction contracts. We're now in version 3 of UCSF's design and construction contracts. This is how we've gotten integrated project delivery into our major projects. So yes, I have to report to my campus leadership. I have to engage with the UC regents. I have to engage with the Office of the President. And then UCSF has a board of overseers that is part of our foundation, because we depend tremendously on major donations. And so there are developers on that board. I would say that the developers don't entirely understand what we're doing, because we have been developing a much more flexible and powerful delivery model than most developers understand. I don't think that's inaccurate to say. We have the best contractors working for us, both at the trades level and at the general contractor level. We have the best consultants working for us. Everybody wants to work for us now, because we try to make durable decisions quickly with a rich information environment and creativity. It doesn't mean we don't run into problems, but we do have an advantage over a lot of developers. Now, we do have a project that we have some developers helping us manage a donor situation with, and they are, I have to say, by all accounts, they're pleasantly surprised and kind of shocked at how well that project was being done. So I hope that that will start to help our board of overseers see a little more how we're doing. But it's a dynamic thing, and people have, my observation is that people have perceptions about project delivery that from the outside that almost never correspond to what's really going on inside, and you guys know that because you're inside it. I hope that our grand experiment, and we really have started to deliver major projects on time or ahead of schedule and under budget, including our $1.5 billion hospital. That story is going to come out, and the pleasure that people have working for us, which I really value, will come out, and will help other people see that you can do it differently. Our prior versions of contracts, the Office of the President will train campuses to use. So UCLA is using our version 2. When we get to road test what we develop, and I have to eat my own cooking. But when version 3 has been road tested and this generation of projects is done, then I really hope that will start the whole UC system in the direction of integrated project delivery and lean construction.
Okay. I think we have time for one more question. Yes.
So, how long will it take real estate developers in the market to recognize the added value through resilience? What's your forecast?
Yeah, well, that's a great question. We can ask that same question about resilience, about sustainability, about LEED certification. 20 years ago, developers didn't want to do any LEED certified buildings either because the public demand hadn't grown high enough that they could then charge for it, essentially, that it was a value proposition for them. As Michael's always said, it starts out as a first cost, lowest cost. But if you can charge for it, then they'll be incorporated. And today, you can go on developers' websites. In fact, we were just on one today, looking at their commercial properties. They do a lot of actually multifamily residential properties. They're here in San Francisco. And you go on their website and you can see their properties, and each one of them has a LEED certified designation by it, okay? They've come to that point where that's what they're going to do on all of their buildings, not because somebody told them they had to, but because now the market is demanding that, all right? And so that's where we need to go with resilience as well. Now, in places like Japan, where they've had a lot of devastating earthquakes, you'll see advertisements on TV for buildings that have base isolation because it's in demand. So people are already building buildings all over the place with base isolation because the public wants it. Developers know that they can charge more. In fact, you can charge up to 40% higher rents or sales costs for buildings in Tokyo, for example. But with the USRC, it's the same challenge, is generating that demand, hopefully before there is an earthquake. And part of that comes in educating the public. We didn't mention this, but a city like San Francisco, 80 to 90% of the building stock was built before modern codes, okay, built before the 1990s or so. And buildings are replaced in the city at maybe 1% a year, 1 to 2%. So it'll take decades and decades for buildings to get up to what we consider modern codes. So when a developer builds a building that is built to the current code, even if it's not built to a higher performance level like with base isolation, but it's built conscientiously to the current code, that already distinguishes it from the majority of other buildings in a city. So just like they're getting these LEED certified ratings, which may not be a LEED platinum level, on their buildings, even getting a USRC certified level, which is essentially a building that complies with the modern current codes, is a way to distinguish it from older buildings. And of course, if you're a developer, you want to build a new building, you want to sell the new building, you don't want somebody buying an existing building. So those are the kinds of inroads we're making. But obviously, absent a major earthquake, it's part of that education. It's part of raising demand from the bottom up. It's about raising demand from tenants, from buyers of buildings, from insurers and lenders that, hey, this resilience is important for me and my business to make sure I can get back in operation, but also so that I don't have to, be saddled with a loan if the mortgage holder, walks away from a building that's got 30% damage and the bank's left with, only owning 80 or 90% of the equity in the building. So that's the process we're going through. But I think there's an opportunity to make inroads with this comparison of current older designs and what you get with even the newer modern codes. Ron?
Given this is great discussion on the issues, I think resilience is the new sustainability. I think it's going to take our profession and as a whole, the architectural and the engineering profession, to move this forward. I think it's an important movement. It's back where sustainability was in the early 90s. And I would hope that our architectural colleagues, the engineering profession, as you can see, got this underway, but it's not going to take off unless it's embraced by the construction industry as a whole. I think it's really important that you all seriously think about getting your firms involved, because it's that combined effort, and we don't need, took the US GBC about 15 years to really get sustainability to where people understood what it is. We can't wait that long for resilience. This is way more important when we're building new buildings, to have them to be better performing than our code design buildings. So I hope this has inspired you as our colleagues in the architectural profession to join with us and become members of the USRC, and let's make this as broad a movement as we possibly can, because it's really important for our communities. And together, I think we can do great things.
Thanks, Ron. That's a great segue to wrapping up our presentation today, is that we have several great architectural companies that are involved with the USRC, like SOM, like HOK, like LPA and others. But the more architects that help support the work that the nonprofit's doing and are also involved in the development of the actual technical standards, especially as we move into other hazards like wind and flood, the better we're going to be able to get the word out and generate that demand. So please do visit our website. We actually just revamped our website. It looks pretty nice. You can look at more of what the USRC is doing, read some of the newsletters that we produced. Y'all also can see opportunities to join and support what we're doing. We really do need your help. Like Ron says, Ron is the chairman of our board, by the way, and one of the co-founders along with me. But it is vital that the AE professions really take that first step. Sometimes we can't wait for the demand to come along. We have to be out there pushing what we know is right, and the demand will follow. So look, thank you again for coming. I think we'll be hanging around for another few minutes if you have any other questions, but really it's been our pleasure to speak with you tonight, and go back and talk to your offices. Thank you.